Okay, so there you go. So what happens is that now I'm going to measure a performance of cars. So first I'm going to throw in into one factor. I'm going to call this as factor A. So for example, if I have different type of, let me pick one brand. For example, let's say if I were to pick Honda, so there are various type of cars in Honda, okay, various models. So it could be HRV, it could be a CRV, it could be a Civic, and it could be a CT and so on. For example, let's say I'm going to choose this four model, HRV, CRV, Civic, and City. So if I were to compare the performance between all these four models, so this comes from one factor, and my factor is called as car model. Okay, and under car model, I have four categories. So 1, 2, 3, and also 4. So if I were to compare between their mean, so I'm going to call this as mu1, this is going to be mu number 2, mu number 3, and mu number 4. And if I were to compare whether or not these are equals, so this is going to be ANOVA. I only have one factor, and I'm going to compare the between all of them. So this is going to be ANOVA. That will be the idea. But for example, let's now, I'm going to throw in another factor. So instead of having only one factor A, I'm going to have two factors. So which is going to be factor A and also factor B. Let's suppose factor A is going to be car model. So factor B, what should I use? I'm going to pick a tire brand. So I'm going to stick to the previous car model. So I'm going to have HRV, CRV, Civic, and City. And for the tire brand, so the thing is that I noticed that even for Honda, for different type of model, so they use different type of brand. For example, I drive a Civic, and when I got it from the factory, so it was attached. So I got a Continental tires. My housemate, she drive a HRV, and they actually put a Yokohama on the car. So let's say I'm going to have a Continental, Yokohama, and let's do another one. So let's say it's going to be Michelin. All right, so now for factor A, I have four categories, 1, 2, 3, and 4. So I'm going to have four categories. So my value of A, small a, which represent number of A categories, so that is going to equal 4. So this is my factor B. I have 1, 2, 3, three categories in factor B. So my small b value, which is the number of categories for factor B, so the number is going to equal 3. Okay, so what I'm going to do is, if I were to have two factors like this, so this is going to be two-way ANOVA. So we are no longer going to be comparing mean, so it's not valid for this case. We don't compare mean. But what we're going to do is we are going to have a look whether or not these two are actually related. So that's the type of car and the type of brand of tire that is attached to the car has somehow affected the performance of the car. So we are going to look whether or not they actually have interaction between each other, between these two factors. So that will be the difference between ANOVA and two-way ANOVA. So ANOVA measures mean, whether or not they are equal. So two-way ANOVA, they measures interaction, whether the two factors is actually related to each other, whether there's interaction going on between them. Okay, that will be the idea. So that is the purpose of one-way and two-way. So now we're going to have a look, how do we tell the number of treatments for each of the type of analysis. Okay, for the number of treatments, one-way ANOVA, so we use K to represent the number of treatments. So K is going to be number of category in factor A. So if I were to refer back to my previous example, for this case, what is going to be my value of K? So I have four categories, so therefore the K value is going to equal 4. And for the case of two-way ANOVA, so the number of treatments is going to be measured by having A multiplied by B. So A is going to be a number of categories in factor A. So B is going to be number of categories in factor B. So this I've written over here already. For the case of factor A, we have 4 categories. For the case of factor B, we have 3 categories. So if I wanted to know what is going to be the number of treatments, so that is going to be given by A multiplied by B, so which is going to be 4 multiplied by 3. So for this case of two-way ANOVA, so I'm going to have 12 treatments altogether. All you have to do is multiply the value of A and B. Okay, so that will be the second difference. The third difference is that, okay, for each treatment, for one-way ANOVA, so number of replicate, so does not have to be the same. So what is number of replicate? So number of replicate means for each of the treatment, how many samples are taken. For example, let's say if I were to refer back to the previous example, for HRV, So I'm going to take the data from 4 cars. So 1, 2, 3, and 4. So from CRV, I'm going to take a sample from 3 different cars. So 1, 2, and 3 Civic. I'm going to take 2, 1 and 2, and City. I'm going to take 4, 1, 2, 3, and 4. So this is going to be my replicate. From the first category, I take 4. From the second category, I take 3. From the third, I take 2, and from the fourth, I take 4 samples. So this are called as being the replicates. How many samples are taken from each of the category? So the thing is that for the case of one-way ANOVA, so it doesn't have to be the same. If you notice here, I took 4, 3, 2, and also 4. It doesn't have to be exactly the same number for each replicate for each of the category. But for the case of ANOVA, so if you have a look at here, so there are 12 treatments for ANOVA. So what are going to be the treatments? So the treatments are going to be for HRV. I'm going to have HRV Continental, HRV Yokohama, HRV Michelin. So this is already 3 treatments. And the same goes for CRV. So it's going to be Continental, Yokohama, and Michelin. So this is going to be 4, 5, 6 treatment and so on. Okay, for the case of treatment of replicate, for each of this car over here, so for HRV that has Continental cars, for example, I'm going to take 2 replicate. For the case of HRV with a Yokohama tire, so I'm going to take 2 replicate. This is going to be 2 as well. This is going to be 2, and everything has to be 2. Okay, the main point is that for two-way ANOVA, all the replicate has to be the same. It cannot be different like what we have for one-way ANOVA. That will be the difference. Okay, what else? So in terms of the hypothesis testing, when we go from chapter 5, 4, 5, and 6, everything you do is going to be hypothesis testing. So the step is going to be exactly the same as what we have discussed in chapter 3, but the only difference is that every single hypothesis testing that we have seen in that we are going to see in chapter 4, 5, and 6, everything is going to be a one-tail test. So that's the good news about it. Okay, so for the case of one-way ANOVA, how many hypothesis testing? So this HT over here, so it stands for hypothesis testing. So for the case of one-way ANOVA, you're only going to have 1 hypothesis testing. Okay, so I'll put over here and highlight that. So it's going to be only 1 of them. So you are going to test either the means are equal or at least one of them is not equal. So when we say that at least one of them is not equal, can we actually tell which one is not equal? No, we have no idea. So we only know that at least one of the mean is not the same, but we couldn't tell which one is actually not the same. Or it could be also that none of them are going to be the same. They could be all different. So that is possible as well. Okay, but the main point is that we can only test whether all are equal or not all are equal. So that is the only thing that we can do for one-way ANOVA. But we couldn't tell which one is different or like how many of them are different. Is it that only 1 is different? Is it 2 is different? Or is it all of them are different? So we have no information about all of that. Okay. And for the case of, what do you call that? Two-way ANOVA. So how many hypothesis testing there are? So it depends on the question itself. So the minimum hypothesis testing you could do is going to be 1. The maximum is going to be 3. The easiest way to tell is from the marks itself. If the question actually gives you only 4 to 5 marks, there's like you only will have to do 1 hypothesis testing. But if the question actually gave you 12 to 15 marks, that's definitely going to be 3 hypothesis testing. Or it could ask you for 2 as well. So it depends on the cases. Okay, how do you know whether you have to do 1 or you have to do 3 or you have to do 2? So it's going to be based on your first test. So the first test, what we're going to do is we are going to test for interaction. So if you have listened to the video for two-way ANOVA, you have known. So what is the test for interaction? If the interaction exists, if we come up with the conclusion that yes, there is an interaction between factor A and factor B, so what you're going to do is you're going to stop the calculation, that's it. So when interaction exists, you stop right there. So you are done with your hypothesis testing. However, when you do the hypothesis testing and it comes to the conclusion that factor A and factor B, there is no interaction, you have to proceed with marginal effect. So you have to test for factor A individually, and then you have to test for factor B individually. So testing for factor A and factor B individually, so that is called as testing for marginal effect. For example, if the question said So test for marginal effect of this analysis. So it means that you have to test for factor A and factor B individually. So you don't test for the interaction, right? So whether you have to do 1 or you have to do 3, so that is going to depend on the conclusion that you get from the test of interaction. Okay, so the steps on how do you do the hypothesis testing for ANOVA is going to be pretty much the same idea of what you did in chapter 3. So step number 1 is going to be stating the hypothesis. There will be H null and H interactive, like what alternative, like you always do. Saida, can you please mute your
Oh, sorry, madam.
Yeah, it's all right. Okay, so that will be step number 1, hypothesis. So step number 2 is you're going to find the test statistics. So this is going to be our test statistics. But there are 2 ways of actually doing that. Remember, I've actually listed out, if you have seen my previous note in chapter 3, so we have either you have to use test statistic, you can use p-value, and the other one is you can use confidence interval. But for the case of ANOVA, so you can either use test statistic, which is f-test, or you can also use the p-value. Okay, so it depends on what the question asks. So usually the question is going to state whether you have to use f-test or whether you are going to use p-value. If the question doesn't state, then it's up to you. If you ask me which one I preferred, I would definitely go for p-value, because when I use p-value, I don't have to bother finding for the critical value. But if you use the f-test, you have to compare the test statistic with the critical value. So it could be quite complicated over there, and you could get the high chance of getting your answer wrong. So therefore, I would prefer to use the p-value. However, so you can only get a p-value from an Excel output. If there is no Excel output given, then there's no way that you can come out with a p-value. Okay, so therefore it depends on the question that they give you. And of course, from that, you're going to decide whether you're going to reject or do not reject. So if you use the f-test, so what happens is that you're going to do a right tail test. If your value of test statistic is greater than the critical value over here, so you are going to reject. It's a right tail test. Or if you use the p-value, so if p-value is less than alpha, you reject. If p-value is greater than alpha, you do not reject. So this is definitely easier. I don't know. Personally, I think it's easier, but you can do whatever that you're most familiar with. And of course, after we have decided whether we're going to reject or do not reject, so we can come out with a conclusion. So what does rejecting means? What does do not reject means in terms of your hypothesis? Okay, before I start with explaining the table over here, so is there any question about what I explained so far in terms of one-way ANOVA and two-way ANOVA? Anything that confused you?
No, miss.
Mm-hmm. Okay, so if everything is clear, I'm going to proceed to this table right here. So this is called as one-way ANOVA table. So we have a different table for different analysis, one-way and two-way. So this is how one-way ANOVA table looks like. So if the question asks you construct an ANOVA table, so this is what you have to construct. Usually for the previous semesters, because we are doing like our assessment face-to-face, you're not allowed to check the book and such. So what happens is that students have to memorize this table, but that's not going to be the case for you at the moment, because we are doing online learning, and even your final exam is going to be open book. So therefore, you don't have to memorize this, but you have to know each of the element that we have in the table. Okay, in the first column over here, so this is going to be source of variation. So the first one is called as sum square of treatment, SSTR. Over here is going to call as sum square of error, SSE, and the last one is called as sum square of total. So I'm pretty sure that you already seen this already in the video, so I'm not going to explain everything in detail. So this will be formula for each of them, okay? And of course, this one is going to be the total, so meaning that if you add these two up together, so it's going to equal this value. The same goes for this one, so it's going to equal the value at the bottom. But I want you to be able to know this very well about k minus 1. So k is going to be the number of category minus 1. That is going to be the degree of freedom for treatment. And then you can have n minus k. So can somebody tell me what is the difference between if you notice in this formula right here, so some of them are using small n and some of them are using capital N. Can somebody tell me? So what is the difference between small n and capital N? What does it mean by small n? Yes, mother.
Yes. If I'm not mistaken, the small n is for the sample.
Yes, it's number of sample of what?
Number sample of the population.
Okay.
Good. I don't know.
Okay, nice try by the way. Yes, it is number of sample, but it's actually number of sample from each category. So it's going to be from each category. Okay, if I were to refer back to my previous example, so remember I take different number of sample, different number of replicate from each of the category in my Oneway ANOVA. So here I took 4 in the first category, so my n value is equal 4. So in the second category, I took 3, so my n is going to equal 3, and this is going to equal 2, and this is going to equal 4. But to differentiate them, we put n1 to know that it's n from the first category, n2, second category, n3, and also n4. So that is what the small n stands for. So it's number of sample from each of the category. But what is the difference between the capital N and the n? And the small n. So the capital N is going to be the grand total. So what is grand total? So grand total means that you are going to add up all the sample from each of the category. For example, so let's say that from the first category, I have 4 sample. From second category, I have 2. And from the third category, I have 3. So when I wanted to calculate the grand total, I'm going to add them all up. So I'm going to have 4 plus 2 plus 3 from each of the category. So my grand total value, that is going to equal 9. So that is the difference between the small n and also the capital N. Okay, so that is going to be for the degree of freedom. And of course, when you add these two up together, so you will get capital N minus 1. So that is going to be the degree of freedom of the total. And how do you calculate the mean square? All you have to do is take this value, divide by the degree of freedom. So that is going to be your mean square. And the same goes for mean square error. You take the sum square, you divide by the degree of freedom, and you will get this value right here. But for the case of total, no, we're not interested in the mean square, so you don't have to find the value right there. And then this is going to be your test statistic value. So we're using F-test for the case of ANOVA. This is actually a test statistic. And the formula is given by mean square treatment divided by mean square error. So you take the value at the top, you divide by the value at the bottom, and then you will get the value of test statistic. And of course, the critical value is the value that you get from the statistical table. So this is going to be from the table. So the first element that should be there, so let me write it. It's kind of small right here. So it's actually F alpha k minus 1 and minus k. So the first element is given by the value of alpha. So you'll find this in the question. The second element is going to be k minus 1, which is the value right there. And the last element is going to be n minus k, so which is the value that is right underneath. So that is going to be a critical value. So all you have to do is then refer to the statistical table. So it's going to be somewhere over here. So everything with the F-test. So the value of alpha goes to the top. So this is going to be the second element, and this is going to be the value of the third element. So I'm pretty sure you have seen this before. You already used the F-test for the case of hypothesis testing for variance. Okay, so that is going to be for Oneway ANOVA table. But in terms of the Excel output, so this is how the Excel output is going to look like. So between groups over here, so refer to the treatment, and within group refers to the error that we have over here. So basically, they are actually the same. Okay, but of course, everything is already given. So when the question gave you the Excel output, you don't have to calculate for anything. You just have to extract the information from the Excel output. And the thing about Excel is that it gives you everything. It gives you the test statistic value. So this is actually the test statistic value. and it even give you the p-value, so meaning that you have a choice. So you can either use the test statistic or you can also use the p-value. Okay, so if you use the p-value, so you just have to take the value and compare that with alpha. So here I get that my p-value is smaller than alpha, so therefore we are going to reject H null. And the same goes for what happened over here when I use the f-test, when I catch this. So my critical value is given by 5.2922, and my f-test is definitely greater than that, so therefore we also have to reject H null. But the thing is that you don't have to use both value, you only have to pick one. Either you use the f-test or you use the p-value. You don't have to use both of them. But the main point is that whatever value do you pick to do the test, both of them are going to give you exactly the same conclusion. If reject, both of them are going to reject. Do not reject, both of them are going to be do not reject. Okay, and this is going to be for two-way ANOVA table, of course, so it's going to be more complicated. But for two-way ANOVA, for one-way ANOVA, yes, you have to know how to construct the table from scratch. But for the case of two-way ANOVA, you don't have to. So when we ask you the question for two-way ANOVA, so we're going to give you an Excel output that looks like this. So it's going to be written ANOVA. How do you differentiate whether this is output from one-way or two-way? So for the case of output for two-way ANOVA, so you're going to have a row over here, so which writes interaction, because for only for two-way ANOVA that we can test interaction between two factors. Okay, so but you have to know what is going to be the element in each of the table, because sometimes the question could give you something like this. So let me show you the example. So this is actually the final exam question from last semester. So they actually give you an output table from Excel, but they blanked some space. So they ask you what is going to be the value of P, what is the value of Q, R, S, T, U, V. So you have to know how to find each of those values. You have to know where you find information in order to find them. So that is why you have to know the table. You don't have to know how to do the table from scratch, but you have to know how to use each of the element in there. So I already explained to you what is A and what is B. And for the case of interaction, so the degree of freedom is going to be the product of both of them. A minus 1 multiplied by B minus 1. And here for the case of error, it's going to be AB multiplied by R minus 1. And what is R? So R represents the replicate. Remember I explained to you before, for the case of two-way ANOVA, so how many samples do you have to take from each of the treatment? They have to be exactly the same. So how many samples are there? So that actually refer to the replicate. So if I take 3 for each of the treatment, so that means that my R value is going to equal 3. If I take 2, that's going to be R equal 2 and so on. And the last one, the degree of freedom is going to be A, B, R minus 1. But the idea of mean square and so on is still going to be the same. You take this value, divide by degree of freedom, you will get mean square for each of the row right here. The formula is going to be the same. But for the case of f-test, because remember we're going to have 3 hypothesis testing. So when you wanted to know what is going to be the critical value for the row effect, so you take this mean square, you divide by the error, so which is going to be right at the bottom. So when you wanted to know the test statistic for column B, so you take the mean square of B, again you divide by the mean square error, so which is right at the bottom. And when you want to know the interaction, again you're going to divide by the MSE and you will get the critical value. Okay, and this is going to be, so for each of the test statistics, so the critical value is going to be different. So that is why, so instead of like doing your test, okay, but the good news is that when you are given an Excel output, Excel would generously give these values already. You don't have to find it in the book, so you are already given the value. So if you plan to use f-test, or the question actually asks you to use f-test, so the critical value is already given. You don't have to find it in the book. But the easiest way, as I mentioned to you just now, is by using the p-value. It's going to be the easiest way. Okay, so before we start with this particular example, do you have any questions so far about the table? So I guess not. So I'm going to proceed to this particular question. Okay, this is going to be one-way ANOVA. So it says an acoustical engineer is studying noise level in center cities on weekdays. So she take measurements each day of the weekday for 4 weeks at the same intersection and at the same time. The following measurements were taken. Okay, so these measurements, that what are we taking over here? So this is going to be what we measure, the data that we collected. So the data that we collected, so that is going to be known as the dependent variable. So this is what we collected. So data collected. So that is going to be our dependent variable. So for this case, what is our dependent variable? So it's going to be the noise level. Those are our independent variable. And what is going to be our independent variable? What is our factor? So this is actually going to be our factor. So what we vary in the question, what we vary is going to be the days. So we have 5 different days, which is Monday, Tuesday, Wednesday, Thursday, and also Friday. So this is going to be our factor. And of course, for this case, as I mentioned to you just now, this is going to be one-way ANOVA because we only have one factor, which is going to be days. And we are given the most important information over here. So we also been given the fact that sum of xij square, so that is going to equal 83,641. Okay, let's answer question number A1. So what is the variable in the study? So actually this question is not very clear. So we have 2 types of variable, independent and dependent. So usually the question should state, so which one do the question ask you for, independent variable or is it dependent variable? So let's put both for this case. So the independent variable is going to be our factor, so which is going to be the days. So that is going to be the independent variable. And dependent variable is going to be the data that we collected. What data do we collect? So it's going to be on the noise level. So that is going to be the dependent variable. Okay. And then question number 2 asks, what is the factor in the study? So I mentioned to you before. So this is going to be the factor, things that we vary in the question that has different category. So that is going to be our factor. And for this case, it's going to be days, right? And then next question says the construct ANOVA table. So this is basically not there. I put it there so that we can easily refer to the formula. But in real life, if we were to ask you this question, so this table is not there. So just stop until here. Construct ANOVA table, and that's it. Okay, before I proceed to showing you this example and constructing this ANOVA table, can somebody tell me what is the first step that I should do? What should I do with this data right when I get this? Anyone who have actually listened to the video? So what is the first step that you have to do? So when you wanted to calculate for one-way ANOVA?
Total each category.
That's right. So what you have to do is, so you have to total each of the category. Now what I have is, I have 5 category. So 1, 2, 3, 4, 5. So if you notice in this formula, so there is a formula that states this. So which is xi square with a dot. So what does the dot means? The dot means total. So if I write x square 1 dot, so I have to find the total for all that has to do with treatment number 1. And I have to square the value. So that is what the formula means. So that is what I did over here, is I sum up everything that comes from the first category. So I have 66, 71, 70. So when I get that for the first category, the sum, the data is going to equal 207, just to save time. I don't want to wait for you to calculate all that. So for the second category, so I add them up together as well. I got 289. So I do the same for the third category. I got 278. And then I do it for the fourth and also for the fifth category. And after I have all these values, I need to find what is going to be this, which is x dot dot. Can anyone tell me what does this x dot dot means? What is this symbol represents? What is the name of this? Anyone?
Grand total maybe.
Exactly. So it is called as the grand total. So what is the grand total? So grand total is when you actually total up everything. So when I total up everything, so this one plus this one plus this one plus this one plus this one and plus this one, so I will get the value of the grand total. So that is what it means by the x dot dot. Okay, can somebody calculate for me what is the grand total for this case?
1191.
1191. Is that what you got?
Yes.
Okay, so right, got a value of 1191. Okay, so now that I have this information already, then only I can start calculation by using the table. So I'm going to start using the table right here. So first of all, so I'm going to start calculating the sum square treatment, so which is going to be the element right there. So according to the formula, so when I wanted to find the sum square treatment, I have to take the treatment for each of the treatment. I have to square the value of the sum and divide that by the sample size of each of the treatment. So that is the difference between the small n and the capital N. So okay, I'm going to start with treatment number 1, so which is 207. So I'm going to square the value. So it's going to be 207 square over. So what is going to be the n value for the first category? So I have 1 through 3. So my n1, the value is going to equal 3. So therefore, this is going to be over 3. So plus, then I'm going to move on to the second category, so which I have a total of 298, and my n value is going to equal 4. So that is going to be 298 square divided by 4. And I'm going to do all the same for the rest of the categories. I'm going to have 278 square, and that is going to be divided by another 4 again. And then I have 140 square. So how many samples are there? So I got 2 of them for the first category. And then the last category, I have 268 square, and I have 4 categories for this case. I have 4 samples, 1, 2, 3, and also 4. And that is going to be for the first part of the formula, first summation. And then I'm going to have minus. So I have x dot dot square, that is grand total, which is 1191 square. So divide by the capital N. And for this case, when I wanted to know what is going to be the capital N, all I have to do is total up all the samples. So first category, I have 3, 4, 4. So that is going to be 11. This is going to be 13, so plus 4. So that is going to be 17 samples in total altogether. So what is the value of my SSTR? Can someone calculate that for me?
One hundred 20.9411.
94?
11.
11. Okay, so your friend got a value of 124.9411. So actually, I got a value of, let's put a 2 at the back. So it's going to be 124.9412. So that is going to be the sum of square treatment. And then I'm going to calculate the second element, so which is going to be sum square total. Okay, the thing is that, why do I skip the sum square error? Because when I wanted to calculate sum square error, I need to first find what is going to be the sum square total. So that is why I skip that and proceed right away to sum square total. So sum square total is going to be more complicated. If you were to calculate this from scratch, it's going to be so much work. But luckily, so this bit of the formula, so which is the summation of each of the data being square, so it is already given over here. So that the value is going to equal 83641. So actually what you have to do if the value is not given, so you have to square all of this. So you can have 66 square plus 71 square each of the data until the last one, so which is going to be 67 square. So there are 17 sample altogether, so meaning that you have to square each of them and add them up for all 17 numbers. So that is going to be definitely going to be a lot of work. So usually for this case in the test or exam, we would give you the value because we don't expect you to spend that much time on the calculation. All right, the good news is that already given. It's going to equal 83641. So I'm going to have 83641 minus. So according to the formula, the last bit is going to equal this, which is going to be 1191 square divided by 17. And the value of, what is the value of this? SST?
$200.9411.
Okay, so it's going to be 200.9411. You got 11 as well?
Yes.
So let's use one over here as well if that's the case. Okay, so it's going to be 200.9411. So now that we already have SST, we can proceed to the value that we left before, which is going to be SSE. So which is given by SST minus sum of square treatment. So SS total is going to equal 200.9411 minus sum square treatment. So that is going to be 120.9411. So that is exactly the same at the back. So I'm going to have 200 minus 120. So that is going to equal exactly 80. That is going to be our sum square error. Okay, let me cut this table and bring it up. I'm going to cut it. Now let's put it here. Okay, so there goes my table. So I'm going to fill it in now. So based on the value that we got. Okay, so sum square treatment that is going to be given by 120.9411. Error is going to be given by 80. And the last one is going to be 200.9411. And then I'm going to start filling in the degree of freedom. Can somebody tell me what is going to be the value right here? So what is going to be the degree of freedom for sum square treatment? So this is going to be the formula K minus 1. What is the value of K minus 1? What is our K value for this case?
Do you change that? 5.
K is equal 5. We have 5 categories. So K minus 1. So for this case, our degree of freedom is going to equal 5 minus 1. So that is going to equal a 4. And then for sum square error, so the formula is going to be given by n minus k. So n minus k. So what is the value of n minus k? So our n value is equal 17. So minus 5. So that is going to equal a value of 12. And the last one, so which is going to be sum square total, is given by n minus 1. So we know that it's going to be 17 minus 1 for this case, it's going to be 16. And of course, you can check so whether or not your calculation is correct. So you can simply take this value, add that amount with this value, and you should get the total value. So 4 plus 12, that is indeed going to be a value of 16. Okay, so now I'm going to find the mean square. As I mentioned to you before, finding the value of mean square is pretty easy. All you have to do is take this value, so divide by the degree of the freedom. For this case, it's going to be, what value is that? 120 from 0.9411 divided by 4. So that is going to be 30 something, I suppose. Can you calculate that for me? It's going to be 30 point what?
$2,353.
Okay, 30.2353. Can somebody calculate for me what is going to be the mean square for sum square error?
$6.6667.
Okay, that's going to equal 6.6667. All you have to do is you take 80, so you divide by the value next to it, which is going to be 12. So it's going to give you a value of 6.6667. And for the case of total, we are not interested in the mean square, so the value should not be there. So even this 2 box over here, so it should be, you don't have to fill it with anything. So be none filled in the column itself. And then now that we have all these values, we can straight away find our test statistic value. All you have to do is take the value at the top mean square, so divide by the value at the bottom. So that is going to give you a value of 4.5353. So that is going to be our statistical value, or the value of our test statistics. Okay, now that we already have the table, then only we can start with the hypothesis testing. So step number 1 is going to be hypothesis. So I'm going to write down my H null and also H alternative. Okay, the thing about ANOVA is that you can choose. Either you want to write your hypothesis in terms of symbol, or you want to write it in terms of words. So both of them are actually accepted. For example, if I want to write it in terms of symbol, I have how many categories? I have K, my categories is equal 5. So we're going to test whether or not each of the categories has the same mean. So the null hypothesis is, we're going to say that all of them are equal. So mu1 is equal mu2 is equal mu3 is equal mu4 is equal mu5. So this is going to be in terms of symbol. Or if I don't want to write it in terms of symbol because I am afraid I would do a mistake in terms of like how many mu should there be, I can also write that in terms of sentence. So I can do it after that. I can write that. So all the means are equal. That's it. So that is going to be my hypothesis testing. Or the alternative in terms of symbol is going to be mu I is not equal mu j, meaning that for one of the, what do you call that, at least like one of the mean is not going to be the same with the rest of the mean. For at least one ij, so what is going to be the value of ij? So it could either be 1, 2, 3, 4, or 5, because we have 5 categories. Or in terms of words, I can write that at least one of the means is different. As I told you before, we don't know how many are different, but we know that at least one is different. So either you write it in terms of symbol, or you want to write it in terms of sentence. That is going to be totally up to you. But when you write it in terms of symbol, so get it right. If there are 5 categories, there should be all 5 means altogether, 1, 2, 3, 4, and 5. So for this case also, when you write at least one ij, so it should be from 1 until 5. So if you written it in terms of symbol, be careful. So the number of k should be the right value. So that is going to be in terms of the hypothesis. And then I'm going to move on to step number 2. So which is going to be the test statistic. So we already got the value. So for this case, test statistic from the ANOVA table. So we obtain a value of 4.5353. But of course, if I wanted to make a decision, I have to compare this with a critical value. So my critical value is going to be F alpha, mu1, and also mu2. So how you get these values? From the table. So what is going to be my alpha value from the question? It doesn't state over here. So what is going to be my value of alpha? So therefore, automatically, we're going to assume that we're looking for F 0.05. And what is going to be the new one? According to the table, so the new one is going to be this one, k minus 1. And the third element is going to be n minus k, which is going to be the second degree of freedom. So just extract that from the table. So for this case, I'm going to have 4 and also 12. So therefore, I'm going to have 0.05, 4, and also 12. And the value, what's going to be the value of this? So that is 0.05. This is 0.005. So I have to look at it very carefully. So where is 0.05? So it's going to be somewhere over here. And that is going to be a 4 and 12. So this is my 4. So this is my 12. So this is where it intercepts. So intercept is going to be a value of 3.2592. 12. Why is it that I've written over here 4 point something? Can someone check the statistical table for me? So is this right? That's going to be this value? 3.2592. Or is it written in the question? So what is our alpha for this case? Is it written? No, it's not written. It just says construct the ANOVA table. So yeah, that should be our value then. Or did I? No, I know what happened. So the question is actually down here. So it says over here that the test hypothesis that the mean data provided by noise level is the same for all days at 0.025 level of significant. So when I put my notes, I'll put that up there later. So this is what we're testing. Okay, so basically, so this is no longer going to be 0.05, but this is going to be 0.025 for 12. Is that right? Yeah, it's going to be 0.25 for 12. And according to the table, 0.025 for 12. So it's going to be somewhere up here. No, it's 0.01, 0.02, 0.03. I know what happened. This is not the value of a test. It is. No, this is 0.025.
Page 44. Page
Yeah.
44. I mean, right.
Yeah, exactly. It's on page 44. This is the value. So it's going to be 4.1212. So I'm going to put right here, it's going to equal 4.1212. So therefore now, remember the test in chapter 4, everything that you test is going to be a right tail test. The same goes for chapter 4, chapter 5, and chapter 6. So you don't have to bother. So what tail is it going to be? Everything is going to be right tail test. So this over here is going to be 4.1212. So therefore, when I make a comparison, I can write that. So my test statistic value, my F test value, is going to equal 4.5353. So that is actually greater than F 0.025 for 12. So which is equal 4.1212. So therefore, it's going to fall into this region. So that is the rejection region. So therefore, we are going to reject H null. So what does it mean by if we reject H null? So if we reject H null, so meaning that H null is wrong, so we're going to take the alternative. At least one of the mean is different. So we're going to answer the question. So the question asks you that the mean data is the same for all days. Okay, we're going to say that at alpha equals 0.025. So we do not have enough evidence that the mean level of noise on each. So just basically just telling, so at alpha equals 0.025, so the mean is going to be different. Not all of them are the same. So that is going to be the conclusion. So basically, if you understand what you did in hypothesis testing, so this is going to be a piece of cake to you because you don't even have to come up with the hypothesis. So the hypothesis is already fixed. It's always going to be H null, all the means are equal. Alternative, at least one of the mean is not equal, right? So that is in terms of what you have to do when you have to come out with your own table. Or, so the question could also give you something like this. They give you the table right away. So why don't you read the question first? So it says over here, 4 different types of solar energy panels were measured. So to test the performance on energy absorption. So what we are actually measuring, what data are we collecting? So we are collecting the energy absorption performance. So each type was observed at 5 randomly chosen times and the power was measured. So figure 2 presents the Microsoft Excel output based on the recorded data. So if you have a look over here, so even if the Excel table is already given, so some of the elements are actually missing. So that is why even if you have an output, you still have to know how to use the table. So what is going to be, how do you find each of the element in the table? Okay, so first of all, so we have to, from the question itself, so we have to identify the factor. What is the factor for this case? Can anyone tell me what is the factor? Just by reading that, can you tell?
Type of solar energy panels.
That's right. So that is going to be over here. So the factor is going to be 4 different type of solar energy panel. Okay, so that is going to be our factor A. So if the question asks you what is going to be the factor or what is going to be the independent variable? So this is going to be our variable. So solar energy panels. And what is going to be the dependent? So it's going to be the energy absorption performance. So the first question asks you, how many treatments involved in the study? How many treatments are involved? Remember, the number of treatments is given by K. So what is the number of K? So K is equal what?
K equals to it says 5 randomly chosen time. So 5.
Okay, K is going to be the number of category in the factor. So our factor is solar energy panel, right? How many category are there in the solar energy panel?
4.
5 for 20.
Exactly. Exactly. For this case, so K is going to equal 4. Okay, so that is going to be our value. So what is this actually 5 randomly chosen time? Meaning that, okay, for example, I have solar energy panel. There's 4 of them. I did I write 4? So 1, 2, 3, 4. So these are 4 different types. For type number 1, so I take 5 sample. Here there are 5 sample. This 5 sample. This is 5 sample as well. So that is what I mean by the 5 sample. So how many treatments are there? So it's how many categories are there in our factor. So we have 4 categories. So number of K is equal 4. All right. So next, the question asks you like copy and complete the Microsoft Excel output. So this is actually a previous exam question. So when you do it this test face to face, so what you have to do is you have to copy the whole table and put it into your answer script, but not for this case. So we're gonna answer it right here. So we have to complete the output. Okay, now somebody tell me. So how would I find the element here? What should I do in order to find the element? We don't have any data. So how do I find the sum square of the within groups? So remember what I told you about total?
So we divided.
No, it doesn't involve division. It's a mathematical operation, but not division.
It's minus.
Minus, that's right. So remember, if you add these two values together, so it's supposed to be this, and even the degree of freedom, when you add this up together, it's going to be this value. That's what total means. So therefore, when I want to know what is going to be the within group, all I have to do is take the total minus the 1.6135. So the value is going to be 0.496. So that is going to be the value of the within group. So can somebody check that for me whether it's right, 0.496? Or I can eyeball that.
Yep. Yes.
That's right. So that is going to be 0.496. So that is going to be our sum square for the within group. So now for the degree of freedom. So what is going to be the first element in the degree of freedom? What is the degree of freedom of the between groups?
It's K minus 1.
Exactly. So what is minus 1 for this case?
4 minus 1 equal to 3.
Exactly. So 4 minus 1 is going to equal 3 because for this case, our value of K is going to equal 4. What about within group? So within group is going to be a formula of capital N minus K. So can anyone tell me the value? What is capital N minus K?
16.
So it's going to be 16. That's right. Why is it going to be 16? Because our grand total of sample is going to equal, so for category, each of them has 5 sample. 5 multiplied by 4, that is going to equal 20. So 20 minus 4, that is going to equal 16. That's right. Or even you can check that 3 plus 16, so that is going to equal 19. And I'm going to find what is going to be the mean square. So can anyone tell me what is going to be the value of the mean square? What operation is involved?
Divide.
Okay, so what do I get if I were to divide then?
Zero 0.5378.
Okay, 0.5378. So that is going to be the mean square. And then from those value, I can find what is going to be the critical value. All I have to do is again to divide. So I'm going to have the mean square for between, divide by mean square for the within. So what is going to be the F value? What is the value of that?
17.3484.
Okay, so your friend got a value of 17.3484. So that is going to be our test statistic value. Okay, so we have done question number 1. So we've done question number 4. So those are just very simple calculation. All you have to do is use the formula and use your calculator, and you already got 5 marks. It's going to be as easy as that. And then for the last one, so which is going to award you another 5 marks. So the question asks you based on figure number 2, so which is the output from the Excel table. So can you conclude that the mean power differs for different type of panel? Okay, so we can tell right away. So we are actually wanted to know whether the mean is equal or means are equal or not equal. Okay, so this is definitely going to be one-way ANOVA. But does that mean that you can simply conclude yes, they're the same, yes, they're not the same? No. So when you come across the word can you conclude, so test the fact that, so those are going to be hypothesis testing. So we are going to do all the steps that we are required to do for hypothesis testing, of course. So I will each now. So how many mu will I have for this case if I wanted to write in terms of symbols? So I'm going to have mu1 until, that's right, I'm going to have 4. I'm going to have mu1 is equal, mu2 is equal, mu3 is equal, mu4. Why? Because I have 4 categories. My k is equal 4. And then the alternative, so I'm going to write that at least, if I were to write it in terms of symbol, I'm going to have mu I is not equal mu j for at least 1 I which is not equal j. So what is going to be ij? So the ij value is, it could either be any value 1, 2, 3, and also 4. Okay, so that is going to be in terms of symbol. Or you can also write it in terms of word, like all the means are equal, at least one of the mean is different. So that's fine as well. Okay, so now I'm going to start doing the test. But as I mentioned to you before, so if I were to get to pick between the F statistic and the p-value, I definitely going to pick p-value because I don't have to bother doing the comparison with the critical value. So I'm just going to write down, so what is my p-value? For this case, the p-value is going to be a very, very small p-value, so which is going to be 2.7734. So the exponential, it actually means 10 to the power of -5. So that's what I mean. So basically, this is a value of 0.0000277. So 1, 2, 3, 4, 5. So it being shortened as 2.77 times 10 to the power of -5. And I'm going to compare that with the value of alpha. And for this case, definitely alpha is not given. So therefore, that is going to be 0.05. And of course, 0.0000277 is actually much, much smaller than alpha. So should I reject or do not reject? According to the p-value rule. What should we do? Okay, that's right. So if the p-value is smaller than alpha, you are going to reject H null. Automatically, we know that this is wrong. So we are going to take the alternative. So what does the alternative tells you? That at least one of the mean is different. So I can conclude that. So therefore, at alpha equal 0.05. So that's an extra 0. We have no evidence to conclude that the mean power differs for different type of panels. Okay, so we just make our conclusion based on whether or not we reject H null or do not reject H null. So that is going to be our conclusion. And based on that, by just doing that, you already got the 5 marks. And as I mentioned to you just now, if you were to use the F-test, you have to compare it with the critical value. So whether it falls into the rejection or the acceptor region, and then you decide whether you're going to reject or do not reject. But as I mentioned to you just now, so I would prefer, because here the question doesn't state which method to use, so p-value is going to be a more preferable value. So usually when students use p-value, there's higher chance that they're going to get it right rather than using the test statistic value, the F-test. I think that we should discuss one more question before we end. So I'm going to pick this one right here. Okay, can anyone tell me, just looking by the table, is this going to be one way or two way? Just by looking at the table.
Two-way.
Two-way.
Okay, how do you know it's going to be two way?
The interaction.
Interaction.
Exactly, because of the interaction rule right there, we can tell right away that this is going to be a two-way ANOVA. And this is definitely not going to be easy to understand. The statement is, let's read that together. So the statement says that adding glass particles to clay brick may improve the structural properties of the brick. So we're talking about brick. So actually, if we were to add glass particle into the brick, the structure property is going to be better. So an article in civil engineering described experiments, in which the compressive strength was measured for bricks with a varying amount of glass content and glass particle size. Okay, so this already given us what is going to be the factor A and factor B. Remember, factor A and factor B, they are our independent variable. So independent variable, so I'm put over here, is actually the value that we vary. So independent variable is what we vary, what we control. So that is going to be independent variable. Okay, and for this case, what do we control? So we control the amount of glass content, and we also control the glass particle size. So basically, that is going to be our factor A and factor B. So Microsoft Excel output shows all the effects involved between the amount of glass content and glass particle size on strength of the brick. So basically, this is going to be our factor A. So this is going to be our factor B. So what does this factor affect? So they affect the strength of the brick, and this is going to be our dependent variable. So what is measured? So we measure the strength of the brick. So this is our dependent variable. Okay, so that is how the output looks like. So we are given all the information: the sum square, degree of freedom, mean square, the test statistic value, the p-value, and the critical value as well. So you don't have to calculate for anything. All the values are given, so you just have to use that. Okay, so the question says that since there is no interaction effect, so the question already tests you, there is no interaction effect. So does that mean you have to test for interaction again? The answer is no. No need to bother, because they already said there is no interaction. So we just have to use the information. And it says between the amount of glass content and glass particle size. So test. So what do we have to test? So we have to test the effect of glass particle size on the strength of the brick at 1% significant level. You remember the marginal effect? The marginal effect is when we test factor A or factor B individually. So this is what being asked in the question. So that is why marks is only 5 marks, because we are only going to do one hypothesis testing. So what are we going to test? We're going to test whether or not, so which factor is this effect of glass particles? So that's factor B, whether or not factor B affect the strength of the brick. So this is what we're going to do. So now, automatically, when the question state conclude or state test, it's going to be hypothesis testing. So I'm going to start with the H now. So when it comes to marginal effect, so at the top is going to be no effect or there is effect. Which one is that? Can anyone tell me whether it's going to be no effect or an effect for the H now? Okay, so the thing about two-way ANOVA is that when you test for marginal effect, at the top is always no interaction, no effect. So that is always going to be the case for two-way ANOVA for the null hypothesis. So we're trying to test the effect on factor B on the dependent variable. So we're going to say there is no effect of what we're trying to test, which is going to be factor B, glass particle size, on the strength of brick. If you are confused at what I'm writing right now, it means that you haven't studied two-way ANOVA. You haven't watched the video. And the alternative, there is an effect. So that is going to be the only difference between the null and the alternative. There is an effect of glass particle size on the strength of break. Okay, so that is going to be our null and alternative. So remember, at the top is always no, and at the bottom is always the effect exists. Okay, so now because the question doesn't state so what method to use, I'm definitely going to choose p-value. Okay, however, I have 3 p-values to choose from. It's definitely not going to be interaction because we are not testing interaction. But should I use the top p-value or the second p-value? So which p-value are we going to use for this case? Second one? Yeah, that's right. So Adila said second one. That's right. We are going to use the second one. Why? So how do you know it's going to be second one? Usually in the question, so how they are going to put this into Excel is going to be according to what's written. So here it mentions amount of glass content first. So we assume it's going to be factor A. And then only it mentions about the second factor, which is going to be called as factor B. In the case of Excel, it's going to follow that sequence as well. So at the top is going to be factor A, and this is going to be factor B. So we are testing factor B right now, so which is glass particle size. So therefore, we are going to take this p-value, so which is 0.0010 or 0.001. So my p-value is going to equal 0.001, and I'm going to compare that with my alpha, so which is given by 1%, which is 0.01. And of course, 0.001 is smaller than 0.01. So therefore, so we are going to reject H null. Right? So after I decide that I'm going to reject H null, so meaning that this is going to be wrong, the alternative is going to be correct. So actually, the particle glass size has an effect on the strength of the break. So I can see that at alpha equals 0.01. So we have enough evidence, or we have evidence that, so you can say either, we have enough evidence that the glass particle size affects the strength of break. We just want to see that the effect does exist. Strength of break. Okay, so that is going to be our conclusion. So if you notice for this question right here, so actually the two questions are given together. So at the top, we give you a question on one-way ANOVA, and at the bottom, we give you a question of two-way ANOVA. So that is very common. So usually in the final exam, they will be asked together. So at the top, one way, at the bottom is going to be two-way. So you have to know very well how to analyze each of them. And I think that if you have a look at here in general, so how many marks are there? 5. So this is already 15 marks. And I don't think that the calculation is complicated. As long as you read the question, so you know what the question is asking for, so you know which p-value do you have to use, then I think that you should have no problem at doing the hypothesis testing. You've done something that even harder than this in chapter 3. So this is not comparable. So this is actually easier than what we have seen in chapter 3. And of course, there are more questions over here. So this is, which one is the latest one? Yeah, this is the latest one. This is the final exam from last semester. But I am going to leave it to you for you to try. And I'm going to end it here for now. Or else I will end up doing all the calculations. And I don't even know whether or not you understand what's going on. So I'll leave the rest for you to do on your own. And of course, I'll send you the solution later. But before we end, do you have any questions on one-way ANOVA and two-way ANOVA? Are you guys still awake?
So far, not yet, but I think if we do the exercise, there will be questions.
Then you come out with things. Yeah.
Yeah.
Don't worry about that. So yeah, so it means that you haven't done the exercise. Yeah, that's your point. Yeah, that's fine. So now that you have a better understanding on one-way ANOVA and two-way ANOVA, So try to attempt this exercise that I've put together, and I strongly suggest that you should attempt this question because you might come across something similar for the final. I'm not just like compiling this because I want to, no, as I wish, no. So that's the reason I compile this, and if you do the exercise, you would benefit from it. Miss, why there is Excel way of answering ANOVA question? Shafiq, what does it mean? What do you mean by why there is Excel way of answering ANOVA question? Is Shafiq here? I don't really get the question. Because yeah, of course, like there is for statistical analysis, when it is a small data, yes, we do the calculation, we find the formula, but that is not always the case for real life data. For real life data, like the minimum is going to be thousands of data. So for each of the method that we discuss in this course, there's always an Excel way of doing that. So you have to know how to analyze that very well as well. I mean, can we calculate using Excel for final? The answer is no. Like, okay, if you have looked at the question that we discussed just now, so these two questions. So all we did is we give you like a simple statement at the top, and we give you the output right away. So you don't even have data for you to calculate from. You just have to use whatever that is already given. So no, you cannot, unless the question actually state to use Excel, then you cannot use Excel for the final. And for ANOVA, most of the time it's already given. You don't have to bother calculating that on your own. Anything else?
Doctor, I have a question regarding the part 2
Okay, sure.
for that assignment. Yeah.
Mhm.
Shall we write it in the paper by handwriting, or we write it in Word directly?
I'll leave it to you. It's up to you. But if you plan to do it handwritten, make sure it's somebody with a very good handwriting, and I can actually read
In the Word, it's much better, right?
Hmm?
If I write it in the Word, it's much better on the paper
Yeah,
rather
it will
than the
look
paper.
better for me because the thing is that I'll be marking online on Kalam. Like sometimes, like when you use pencil and such, it is really hard for me. I'm getting old here, so yeah, it's a pain having to stare at the screen for
I
that
already
long.
used the Word, but I just asked to make sure.
Yeah, just use Word is better, but I don't mind if you don't have enough time and you think that you just want to send it handwritten. I don't mind as well. So it's up to you.
Okay, thank you
Anything
very
else?
much.
No problem, right? All right, so if you don't have any more questions, so please go back and try to do this problem that I have put together for you. So whatever that we put together over here, this is actually summary of chapter 4. So if you have done all this exercise and you can do it well, meaning that you have already covered everything in chapter 4. Okay. All right, so let's end here for today. So I'll see you on the next session then. All right, so goodbye.
Have a nice day, Doctor.
All right,
Thank
you
you,
guys
madam.
too. No problem.
Thank you, madam.
Thank you,
No
miss.
problem. All
Thank you,
right,
miss.
no problem.